Hello everyone, welcome to GOCC. Today we have Viktória Klász from University of Bonn talking about representation theory and quite a bit of combinatorics, hopefully. Before we start, let's recall a few of our guidelines. We're all learning. Everyone has something to contribute and no one has all the answers. With that, Viktória, let's go.
Thank you for the introduction and thank you for inviting me to give a talk here today. So I'm excited to talk in front of a combinatorics audience because I'm more from a representation theory background, but there exist some connections between representation theory and combinatorics, and I'm going to talk about such a connection today. So in my PhD, no, I cannot change slides. So in my PhD, I care about one particular property of algebras, which is Auslander regularity. Now, as you will see, this has a completely homological algebra definition. So this is where the homological part of the story comes from. The combinatorics, or rather lattice theory side of the story, comes from the fact that we are gonna investigate this property for a very special class of lattices, namely incidence algebras, which come from lattices. And these are the incidence algebras of lattices. And what was discovered by René Marcinzik and Osamu Iyama is that Auslander regularity and some other homological notions translate to some very well-known lattice theoretic objects on this way. Okay, so this connection was known for the last 5 years or so, and the new part of the story is based on our paper with René Marcinzik and Hugh Thomas, which you can find on arXiv, when we introduce Coxeter matrices to the story. And what we show is that we can describe Auslander regularity completely in terms of linear algebra using these matrices, and as a consequence, we can also get new characterizations of the corresponding lattice theory notions. So this is kind of the outline for today. We would like to see some notions expressed in homological algebra, in lattice theory language, and then in linear algebra language. So let me start with the homological algebra side of the story. So during this talk, A will always be a finite-dimensional associative K-algebra, where K is just a field. And let me mention that our algebras will be usually non-commutative. A main goal in representation theory is to understand the module category of an algebra. Here we will only be interested in some the finite-dimensional modules. So there is two kinds of modules which play a particularly important role in homological algebra. These are the projective and the injective modules. We don't really care now about the precise definition. If you want to have an example, you could think of 3 modules, and every free module is a projective module. What we care about today is that projective and injective modules are very well understood in our examples, and often we use these modules to approximate other modules. So in homological algebra, we can sometimes forget about the module itself and just look at its approximation via projectives or injectives, and that carries all the information we care about. So this is how you could think about projective and injective resolutions. So if we take any module M, then an injective resolution of this module is an exact sequence of A modules which starts in M and contains only injectives. Similarly, a projective resolution is an exact sequence of A module which ends in M and contains only projectives. Now, such resolutions are not unique, but there exists a minimal resolution which we usually care about because this carries all the information we want. So it is minimal in a sense that you can find this minimal resolution inside any other resolution. In particular, the minimal resolution has a minimal length. And using this, we can define 2 important invariants, namely the projective dimension of a module and an injective dimension. This will be just the length of the minimal projective or injective resolution. And what you can think about it is that this kind of approximates how far a module is from being projective or injective. So projective dimension of a module is 0 if it is projective, but it could be any natural number. And if there exists no finite resolution, then this dimension is infinite. With this, we can also define the global notion for this. So in an algebra, we call the global dimension of the algebra the supremum of all the projective dimensions of the A modules, which turns out to be the same as the supremum of all the injective dimensions of these modules. And this is again a value in the natural numbers, or it might be infinite. Okay, so this is the background which we will kind of use. And with this, we can then state the main definition for the talk of today. So we call an algebra A Auslander regular if it satisfies two conditions. The first condition is that we want the algebra to have a finite global dimension. Just recall, this means that all these resolutions, the lengths of these minimal injective and projective resolutions have a global upper bound, and they are finite. And then the second condition is a little bit more involved. So this states that for every indecomposable projective over an algebra, if we consider its minimal injective resolution, then the terms which appear in this resolution should satisfy a condition. And this condition is we would like I0 to be projective. We would like I1 to have projective dimension at most 1, I2 to have projective dimension at most 2, and in general, the term which appears in degree m, we would like it to have projective dimension at most m. So this is the definition we will care about. If you are a little bit more familiar with commutative algebra, then you might have heard the definition of regular rings. These rings pop up by looking at varieties, and they are related to determining whether a variety is smooth or not. So if we would assume that our algebra is commutative and local, then this usual definition of regularity would coincide with this Auslander regular definition. So this is also kind of the origin of the name Auslander regularity. Okay, so Auslander regular algebras have many interesting homological properties, but we will only care about one today, which is the following. So Auslander and Reiten showed that if we have an Auslander regular algebra, this comes with a distinguished bijection, which is, I'm going to denote this by phi, and this is a bijection between the isoclasses of indecomposable injective modules and isoclasses of indecomposable projective modules. And this one is defined by taking an injective I, looking at its minimal projective resolution, and sending this indecomposable injective to the last term in its resolution. We know that this resolution is finite because we assumed Auslander regularity, but it is actually quite non-trivial that this last term is indecomposable. So this is a very special property of Auslander regular algebras, that this last term is always going to be indecomposable and that this bijection exists in this way. Because usually if you look at resolutions, the terms just tend to get bigger and bigger and more complicated. So there is a priori no reason for it to end in a indecomposable module. Okay, so this is the main theorem which we will also look at. This, I'm going to refer to this bijection as the Auslander-Reiten bijection. Okay, with this, we are done with the homological part of the story. And our goal for today will be to fill in this table. So in the first column, we have the notions of Auslander regularity, projective dimensions of injective modules, injective dimensions of projective modules, and this map phi. And our goal would be to find analogs in terms of lattice theory, and then finally in terms of linear algebra. Before continuing, do you have any questions so far?
Yeah, sorry. I may have missed it, but what is you said the largest one projective is indecomposable, or
Yes, so if we look at such algebra, so if you look at Auslander-regular algebras, then if we look at a resolution of an indecomposable injective, it will be that the last term is always going to be indecomposable. So this is a very non-trivial result. Usually this is going to be some direct sum of indecomposable modules.
and what does it mean indecomposable? In what sense?
So indecomposable means that so indecomposable modules are like, so every module you can decompose into indecomposables uniquely, and then these are like the smallest building blocks of a module you can think of.
Okay.
Indecomposable is that you cannot write it as a direct sum of two other modules in a non-trivial way.
Okay. Thank you.
Welcome. Okay, if there are no other questions, then I'm gonna continue with the chapter 2. So I told you a lot of definitions in the previous chapter, and I didn't give you any examples, but hopefully we will see some examples now. So in this chapter, L will always be a finite lattice, and Q will be its Hasse-Quiver, and we will have the one lattice on the right-hand side as a running example. So if we have such a lattice, then we can associate an algebra to this, and we can describe this as follows. So as a k-vector space, this algebra is going to be generated by the paths in this Hasse-Quiver, where we also assign a zero-length path to every vertex. And then we also want to introduce some relations between these generators. So we will want to think of two paths to be the same if they start and end at the same vertex. So in the example, you could list its basis as a k-vector space, and then you would have here all the paths of which have length 0, then all the arrows, or the length 2 paths. But you can see that here the paths BD and CE are said to be equal because they start both at 2 and end at 5. And similarly, the length 3 paths are said to be equal. ABD is equal to ACE in the algebra. And then we define multiplication to be basically just composition. So if we have two paths which we can compose, then their composition is their product, otherwise the product is 0. So this definition or this description gives us many examples of algebras, and they are relatively easy to work with because we can also describe the modules over them quite easily. So it turns out that modules over the algebra are going to be the same data as a representation of this Hasse-Quiver. And then a representation of this quiver just consists of the following data. So we assign a vector space, a k-vector space, vi, to a vertex I, and then to every arrow we assign a k-linear map. And we have to take care about one thing. We want to respect the commutativity relations which come from this definition of the algebra. So as an example, you could see that a representation of the lattice above. So here we assign 0 to the vertex 1, and everywhere else we assigned a one-dimensional vector space. Also, the linear maps are just identities or zeros, so it has quite a simple description. And we could check that composing the two maps which correspond to BD would give us the identity, and this is the same as composing the maps corresponding to the path CE. This is also the identity, so we do respect commutativity, and then we get a module. So we can describe every module in this way, which is basically just linear algebra vector spaces and some linear maps. Okay. We said that we particularly care about projective and injective modules. And it turns out that these have a very simple description over such algebras. So there is going to be one indecomposable projective corresponding to every vertex. And you can describe a projective pi corresponding to vertex I as follows. So we would assign a vector space k to a vertex j if there is a path from I to j. Otherwise, we assign 0 to it. And the maps are also relatively simple. So if we assign a map to an arrow which runs between two vertices to which we assign the vector space k, then we choose the identity and 0 otherwise. So you can see here all the indecomposable projectives listed for the algebra which comes from our lattice. So for example, P1 would look like this because from 1 there is a path from every other vertex. So we assign k's everywhere and we choose the identities here as morphisms. And then for P2, there is no path from 2 to 1. So there we should assign the vector space 0, but we assign k's everywhere else and accordingly identities and zeros. This is just to show you that we can actually very easily describe these modules explicitly. Now in the finite world, projectives and injectives are dual to each other. So there is a dual description for injectives. Here the only difference is that we assign a non-zero vector space now if to a vertex j if there is a path from j to I and not the other way around. So in that case, the injective at our vertex I would be one-dimensional because there is only, at vertex 1, because there is only a map from 1 to 1 and from no other vertices. Okay, so we have a description of an algebra. We have talked about modules, projectives, and injectives. And remember, our goal is to describe this Auslander regularity. And for that, we would need to have a description about projective resolutions of injectives and injective resolutions of projectives. And this is exactly what happens in the paper of Osamu Yamba and René Marcinzik. And this is kind of the main result which allows us for these connections between these homological notions and the notions from lattice theory. Because you will see that what they do is they give a formula for an injective resolution for a projective corresponding to the vertex x explicitly, and this description really uses the lattice structure. As you will see, there will be also some lattice operations like meets and joins showing up. Okay, so let's look at this formula a little closer. Now, this resolution, you can see that the first entry, or like the degree 0 module, is always going to be independent of the chosen vertex x. It's always going to correspond to the maximum of the lattice. Now, all the other entries in this resolution are going to depend on x, and for that we need to first define this set S. This is going to be a subset of vertices of the lattice, which are going to be the maximal elements, which are not in the interval between x and the maximum of the lattice. So if we look at our example below, and we look at x when it is equal to 5, then you would see that this interval is just the one element set 5, and the maximal elements which are not in this interval are 3 and 4. So in that case, S is the set of 3 and 4. If x would be equal to 3, then this interval would be 3, 5, and the only maximal element is 4. Okay, and if we have this set, we can describe the other elements. So the elements which show up in the first degree will be injectives corresponding to elements of this set. In second degree, the direct summands are going to be injectives which correspond to meets of two-element subsets of S. Then in degree 3, it's going to be meets of three-element subsets of S, and then in general, in degree D, we will have meets of D-element subsets of our set S. Okay, and this is very nice because this is a really explicit formula. So if we would want to calculate in our example now a resolution for P5, you could either really calculate it homologically. You could also see here as the representations I listed there, but we could also just use this formula and see that, okay, the first, or like the zeroth term is gonna be I5 because 5 is the maximum of the lattice. Then the next term is gonna be the direct sum of I3 and I4 because 3 and 4 are the elements of this set S. And then the last term is gonna correspond to the meet of 3 and 4. So it's gonna be the injective corresponding to the vertex 2. Okay, so this is a very nice formula. However, we have one problem with it. It is usually not a minimal resolution. However, if we assume that our lattice was a distributive lattice, then these resolutions do turn out to be minimal. And in that case, we can also get a formula for the injective dimension of this projective, which is just the length of this resolution. So this will be the cardinality of our set S, which coincides with the number of co-covers of X. So this last part that needs a lattice theoretic argument, you can check that this is actually the map which will give you the bijection between these two sets. But what we see here that now if you would be interested in the injective dimension, for example, of P5, it would be enough to look at the number of co-covers. So in that case, 5 has 2 co-covers, 3 and 4, and it's also the same as the length of the minimal resolution, which has length 2. Okay, so you could ask here how distributivity comes into play, because I think this is one of the nicest connections that somehow distributivity shows up. And let me tell you a few words about this. So the first observation you should make is that this set S consists only of meter-reducible elements, and also that you cannot compare two elements in this set, so this is an anti-chain. And then in distributive lattices, we know that we can express every element uniquely in an irredundant way as meet of meter-reducibles. So what we can deduce from it that if we take two different subsets of S, then the meets of these subsets are going to be different. So in the end, what we get is that every term in this resolution is going to be a different injective module. And this is somehow enough to conclude minimality. That would need a homological algebra argument, but this is how we would use distributivity in this proof. Okay, now this is basically the main theorem, and this we can use to then actually end up by the connections which we are interested in. There exists also a dual version of this statement. As I said, injectives and projectives are dual in the finite world, so we could have a formula of projective resolutions of injectives. In that case, this set S would have a dual definition, and then we would need in this formula to look at joins of sets instead of meets. And in the formula, if we have a distributive lattice, we would have that the projective dimension of this injective uses the number of covers and not the number of co-covers of our vertex X. But everything is very dual. Okay, and then I think the nicest result about Auslander-regular algebras is the following. So we saw that distributivity does play a role in Auslander regularity, and it turns out that it is actually equivalent to Auslander regularity, which is quite nice. Okay, I'm not gonna give you the proof. Let me just tell you of what needed to be, or like how it would go, or let me just remind you basically what Auslander regularity was. So remember that Auslander regularity says that we would like to look at the minimal injective resolution of a projective, and then we would like that the terms showing up, or like the projective dimensions of the terms showing up, satisfy these blue inequalities. And we saw in the previous theorem that in a distributive case, we can describe these resolutions explicitly. And then what remains to us is to look at a general term, let's say in degree D. This will all be of this form. So here, every such term corresponds to a D element subset of S. And then we take the meat of this set, we call this Z. And then what we have to show is that the projective dimension of this injective is at most D. The last theorem also gives us a formula for this dimension, which is the cardinality of this Z, which is defined dually to this S. And then here would come again a lattice theoretic argument, which shows that actually the cardinality of this Z coincides with the size of this subset T. You could again explicitly write down this bijection between the elements of these two sets. And with that, you could conclude that the projective dimension of everything which shows up in degree D is exactly D. So we satisfy all of these blue inequalities we wanted with equality. So, and then this is what Auslander regularity was for us. Okay, so we have now translated one of the notions we wanted. And then the other one we were interested in was the corresponding bijection. And let me remind you how it was defined. So phi, what phi does, it looks at an indecomposable injective, looks at its projective resolution, and sends I to the last term, to the last projective. Now we would like to think of this map a little differently. So we would like this map not to take injectives to projectives, but we would like to see this as a permutation on the vertices of the lattice. And this we can do because we saw that there exists a bijection between injectives and the vertices of the lattice and projectives and the vertices. So this injective I is going to be I of x for some vertex x. And this projective at the end is going to be some p of phi for a vertex y. So we could say that this map phi is actually a permutation on the vertices, which takes the vertex x to the vertex y. And with this, we translated the question, what is this permutation on our distributive lattice, which is given by this way? And some of you might have already seen this definition. So we can actually have the formula here. We know what this does because we had the description for these resolutions from before. So it takes an element x and sends it to the join of all the minimal elements outside this interval from the minimum element of the lattice to x. So this is the dual notion of the set S, which comes here now. And it turns out this is exactly the definition of the rowmotion bijection on a lattice. So I just inserted here the more well-known definition of a rowmotion bijection. So usually it is defined as follows. So you can see a distributive lattice to be given as the set of order ideals of a poset P. And then this map would be defined by taking an order ideal X and sending it to the union of all the order ideals which belong to minimal elements of the poset P without X. And you can see that these two formulas are very similar, and it's very easy to see that they are actually describing the same bijection. Okay, so what we can use these two last theorems for is we can go back to our example and see that this is a distributive lattice, so the corresponding algebra is Auslander regular. This is now a much easier way to determine Auslander regularity than using the definition and computing resolutions of injectives and then resolutions of projectives and then seeing that the dimensions match up or like satisfy these inequalities. And we could also much easier calculate now this Auslander-Reiten bijection phi using the definition of the rowmotion bijection, and we would find that what phi does is it sends 1 to 2, 2 to 5, 5 to 1, and it exchanges these two vertices 3 and 4. Okay, so with this we can fill in the second column in our table. As a recap, we said that Auslander regularity is basically the same as distributivity for a lattice, and if we assume that our lattice is distributive, we can express this invariance from homological algebra just using number of covers and co-covers of an element, and also that this bijection phi is the same as the rowmotion bijection. Okay, before continuing to the last part, does anyone have any questions? Okay, if not, then we can come to our last part and see how we can express these definitions using just linear algebra. So for a moment, we go back from lattices, from incidence algebras of lattices to general finite-dimensional algebras, because these definitions exist there as well. So here we take a finite-dimensional algebra. We say that n is going to be the number of its simple A modules, which is the same as the number of vertices of the underlying quiver or of our underlying lattice in our special case. And then we can construct this Cartan matrix, omega, as follows. So we know that the columns of this matrix are going to be dimension vectors of the projectives of the algebra, corresponding to the projective at vertex 1, projective at vertex 2, and so on and so forth. And the dimension matrix of a module, or the dimension vector of a module, or of a representation of our quiver, is just a collection of the vector space dimensions of the vector spaces we assign to a vertex of our lattice or of our quiver. In our special case in the case when A is KL for a lattice L, this matrix has a particularly easy description. So in this case, the ijth entry of omega is 1 if there exists a path from j to I and 0 otherwise. An important fact about such Cartan matrices is that they are invertible over the integers if the global dimension of our algebra is finite. So in case they are Auslander regular, this is true. And it's also true for every incidence algebra of a lattice. So in these cases, we can define the matrix we are actually interested in, the Coxeter matrix. And this is going to be minus the transpose of omega times the inverse of omega. So this is our definition. And our goal is to detect Auslander regularity and phi on this map, on this matrix, which then, in our special case, translates to detecting distributivity and rowmotion bijection on this Coxeter matrix. The main ingredient of how we do it is we consider a Bruhat decomposition of a matrix. So this definition you might have heard in some of your linear algebra courses. The statement is that if we have an invertible real n by n matrix M, then we can always write it as a product of three matrices, where the first one and the last one are upper triangular, and the middle one is a permutation matrix. This is what we call Bruhat decomposition of a matrix, and the nice thing is that this permutation matrix P in the middle is uniquely determined by M. However, the two upper triangular ones are not unique. And then our strategy is, we look at an algebra, we look at its Coxeter matrix, look at the Bruhat decomposition, and this is where we try to detect distributivity and this rowmotion bijection. So let's look at two examples and see whether we can see something. So the first example is distributive and the second one is not. I have listed here the Cartan matrices, calculated the Coxeter matrices, and I have listed here a Bruhat decomposition for both of them. Now, there's two observations which we would like to make here. The first one is that in the distributive case, we could choose this upper triangular matrix U1 to be the identity. And this basically means that our C is of this form of P times an upper triangular matrix U, which basically means that C is an upper triangular matrix up to reordering its rows. And this we could already see from C. We didn't need to go to its Bruhat decomposition. You could just see that all the different rows have their first non-zero entries in different columns, so it has this form. We could go then to our non-distributive case and see that, okay, this C is not upper triangular up to reordering the rows because the last two rows have both a non-zero entry in the first column, so there is no way to get upper triangular matrix via this. And this basically means that here we cannot choose U1 to be the identity. Okay, the second observation is that in the distributive case, if you look at this permutation matrix P, then the permutation we get from this is the same as the rowmotion bijection, and this is kind of what we hoped for. Okay, before telling you our main result from the paper of together with René and Hugh, let me give you one warning. I described you what we basically want to do. We want to take an algebra, take its Coxeter matrix, Bruhat decomposition, and then look at the permutation matrix we get from here, and then see that whether it's a rowmotion bijection or what form this matrix has. Now, I didn't tell you about that. We actually have here a non-canonical choice to make, and this is the ordering, or like the numbering of the vertices of our lattice, because this will influence in which order we have our columns in our Cartan matrix, which then influences the Coxeter matrix, the Bruhat decomposition, and this permutation P will depend on this numbering. So let me just tell you that if I say we take the Coxeter matrix, we always need to make sure that we tell which ordering to take. Okay, so with this we can come to our final result, which tells us that basically what we have seen in the examples will hold in general. So L is again a finite lattice, and here we say that we choose any linear extension of the order which comes from our lattice L, and with this we can build a Coxeter matrix. And then it turns out that Auslander-Regularity of the incidence algebra, which we know is the same as distributivity of the lattice, is equivalent to our Coxeter matrix having this PU form, which is the same as there existing a Bruhat decomposition of this matrix C, where U1 is the identity. And then the second observation also has an analog. So it turns out that if we choose a distributive lattice, then this permutation matrix from the Bruhat decomposition is always going to be the rowmotion bijection. And in a way, this gives us the correspondence that we wanted. So there is one corollary from this, which is very interesting, namely that I told you that here we can choose any linear extension and we will always get the rowmotion bijection. The rowmotion bijection is not dependent on the numbering or the ordering of the vertices of a lattice. So this tells us that if we take a distributive lattice, then this permutation matrix is independent of the choice of the linear extension. However, this is not true in general. So if we would take this diamond lattice, which is famously non-distributive, then you could calculate a Bruhat decomposition for this and see that in the first numbering, we would get that 3 is a fixed point of this permutation and 2 and 4 are exchanged. So this is something we are not really happy about because 2, 3, and 4 are vertices which should be symmetric in our lattice, but they behave differently. So if you would just choose a different ordering, then you would get that now a different vertex gets to be the fixed point. So somehow this permutation matrix P is not coming or like not tied to our not inherent from the lattice itself. Okay, so finally we can then fill in the table, and in the first row we will find the analogs of Auslander-Regularity, which was distributivity, which was the Coxeter matrix having this PU form. In the second row we just had homological and lattice theoretic analogs, and in the last row we saw that phi is the same as the rowmotion bijection, and we can get the rowmotion bijection from the Bruhat decomposition of such a matrix. Okay, in the final few minutes, let me talk about some future directions because there is a lot of open questions still which one could answer. So we have a general statement about general finite-dimensional algebras in our paper with René and Hugh. Namely, we can show that if we have any finite-dimensional algebra which is Auslander-regular, and we order the simples or the vertices of the underlying quiver in a so-called admissible way, then the Coxeter matrix will always have this PU form, and we also get that this permutation matrix will be our Auslander-Reiten bijection. However, in this general case, we don't get the reverse direction. This will actually be not true. There is a counterexample for that. Okay, and all of these results I told you would motivate for us to do the following. So what we would in the end want is that to have for any finite dimensional algebra, which has, let's say, finite global dimension, we would like to associate a permutation. And we would like this permutation to generalize our map phi. And in the special case, if A comes from a lattice, this would be generalizing the rowmotion bijection. And we could call this the Coxeter permutation if it comes from the Coxeter matrix. Our guess is that, of course, we would like to get this permutation via the Coxeter matrix and the Bruhat decomposition. However, the question remains, which ordering of the vertices or of the simples should we take? Because in lattices, at least, we had some canonicality in this choice, because lattices come with an ordering. However, in general, the algebra is not. So this is kind of the main question which remains, and we would like this ordering to kind of make sense in a sense that we would like to have this permutation generalize our our Auslander-Reiten bijection in a meaningful way. So we want this to have some nice homological properties. And also in lattice theory, we would like to generalize rowmotion bijection in a lattice theoretically meaningful way. So this motivates the question in the lattice case. So for which lattices is the permutation P independent of the linear extension we choose? We saw that for distributive lattices this is true, but for others it might not be. So this question was already, I think there has been some work on it. There was a conference this year earlier where people worked on this question, and I believe that they had some results that semi-distributivity might be the answer. And for semi-distributive lattices, there exists a generalized definition for rowmotion bijection, which then, in that case, indeed coincided with the permutation which we would get from the Bruhat decomposition. So, in a sense, this is a motivation that, okay, this permutation might make sense, or this to define the permutation this way might make sense. And then finally, we said that Auslander regularity is the same as distributivity in lattices. It would be also interesting to know what it is in general posets. So there are posets to which the corresponding algebra is Auslander regular, which are not lattices or not distributive lattices. So this is a question which remains. However, there is very little known because in poset case the resolutions tend to be much more difficult to compute. Okay, this was everything I wanted to say. Thank you very much for your attention, and if you have any questions, I'm very happy to answer.
Thank you so much for the lovely talk. Let's give a round of applause. As Vicky said, questions. Okay, so I am curious about the whole appearance of rowmotion in this context. So rowmotion has been looked at in other cases, right? But then you end up having this appear, like in the case of especially distributive lattices. So you talked about how regular rings talk about some smoothness of varieties, but then you have these lattices which have like a regular thing acting on it. So is there like a geometric interpretation to what's happening, like if you pull everything back?
Oh, that's a very good question. I don't know. I think my geometric knowledge might not be good. But that's an interesting question, whether you could say something about rowmotion in the geometric case. Yeah, I don't know.
I have a question. I was wondering if you could say a little bit more about like the admissible property on the orderings for like you can't just take any old linear extension or order your simples however you want. I was just wondering if you could say something about like what an admissible ordering looks like there.
Okay, so it is basically about another invariant for simples, which is called a grade. And this grade comes up in, also plays an important role in Auslander regularity. This is just another invariant. And then we want the grade to be I think, we want I to be bigger than j if the grade of I is smaller than j or somehow like that. And this works for every finite-dimensional algebra, but this is not the same as a linear extension from a lattice, so this doesn't need to coincide. But the slight problem with this definition is that calculating the grades is basically as hard as calculating whether something is Auslander regular, so there it's not that helpful, but yeah.
Thank you.
worries.
Also, one thing which I don't know if you've looked at, so applying rowmotion gives you the first projective part, right? Or the last projective part, whichever direction.
Yeah.
And rowmotion, we know, can be built up using the toggles action, the toggles on like a post set. Have
Okay.
you looked at what like a single toggle action might do on if you apply it on the injective module?
No, we haven't, but it's an interesting question. Yeah, thank you. Thank you.
More questions, comments? If you have none, then let's give another round of applause. Thank you. And stop the recording.